Now, let's restart our journey to study about physics and aerodynamics. I'm from University Kuala Lumpur Malaysian Institute of Aviation Technology. Before I want to teach you about two lessons today, let me introduce myself. My name is Muhammad Azrul Arif bin Muhammad Azmi. I'm from class 1 AEM1 and my lecturer's name is Miss Azlinda binti Abu Bakar. So, I have two topics that I want to stress it about. The first topic is optics light and the second topic is sound wave. So these are the subtopics that I want to stress it about. So what definition of light? Light is an electromagnetic radiation of any wavelength that travels in a vacuum. So light actually has a speed of about 186,000 miles, which is equal to 300,000 kilometers per second. So, what can you describe about light? Light travels almost a million of times faster than sound, which is, you look about the image below showing the speed of sound 340 meters per second and the speed of light is 300 million miles per second. So, it is proof that light travels almost a million of times faster than sound. So, the properties of light is light as a form of energy. Light travels in a straight line. Light can be reflected. Light can be bent. Light can be refracted. Light has color. Light has different intensities. It can be bright or dim. And light obeys the equation V equal to F lambda, which is V is velocity, F is frequency, and lambda is wavelength. And also the last one is light carry energy from one place to another and on absorption cause a rise in temperature of the absorbing body, which means that it produces heat energy. So we look about example of equation below. Okay, V is equal to 3 times 10 to the power of 8, which is equal to 300,000 kilometers per second, and it is equal to 186,000 miles per second. Example of equation. If F 900 megahertz, what is lambda value? So 3 times 10 to the power of 8 over 900 times 10 to the power of 3, which is equal to 3 over 9 equal to 0.3 meters. That is the value of lambda. So, now we look about the electromagnetic spectrum. Okay, two pictures below show the different wavelength and also the frequency. So, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma rays have different wavelength in meters. So, how about the size of the wavelength? You see, the size from the left bigger, then become narrow, and almost little narrow and so on, right? So, we look about the frequency from the red until the violet one is, you see that frequency for the red color have the biggest wavelength. How about the violet color have the smallest wavelength? You see, this is an example of electromagnetic spectrum. So, what is light dispersion? The separation of light into different color. So, the spreading out of the beam light is called dispersion. This can be seen when sunlight passes through a glass prism. Within the light spectrum, there are 7 colors that can be readily identified: red, orange, yellow, green, blue, violet, and indigo, being difficult to distinguish. When light passes from one medium to another, it is refracted, changes refracted, and also changes in angle. So, the two pictures below show the refraction of different colors. So, the least refracted is red, You see that? The least refracted is red and the most refracted is violet. Same as the graph shown that the violet have the most refracted and the least refracted is red. Okay? The velocity of light in a material and thus its index of refraction depends on the wavelength of light. Okay, now we look about the color combination. Objects appear color because their surface will absorb some of the frequency and reflect others. A red filter, for example, will allow light with the longer wavelength associated with the color red to pass through. Red, green, and blue are known as light primary colors as they cannot be created. Secondary colors can be created by mixing two primary colors. When these three colors are mixed, our eyes see them as white light. So the combination of red, green, and blue is equal to white color. So different color will create when the following colors, red and green, or green and blue, or blue and red, or red, blue and green. Okay, so now let's look about law of reflection. What is reflection of light? The abrupt change in the direction of propagation of light rays that strike the boundary between different media. There are two laws of reflection. The first one is the incident ray, the reflected ray, and the normal to the surface all lie in the same plane. So the second one is the angle of incidence I is equal to the angle of reflection R. This law of reflection applies equally to curved and flat surface. Example reflection of light in our daily life is mirror. If you view from further away, you still see the same amount of yourself. These two pictures below show if you view from further away, you still see the amount of yourself. Okay? So, 8 everyday uses of mirror or reflection in everyday life. First, periscope, reflective clothing, lateral inversion, kaleidoscope, dental mirror, fiber optic lights, one-way mirror, and laser energy displays. Okay? And this is a reflective clothing. This is kaleidoscope. This is the one-way mirror. Okay, and so on. So, the curved mirror. What if the mirror isn't flat? Light still follows the same rules with local surface normal. Curved mirrors are of two types. Curved mirrors are of two types. Sorry, my typo. So we have concave and convex. What is concave mirror? This is a concave mirror. This is a convex mirror and this is concave mirror. What is concave mirror about? It's a surface that is shaped in towards the middle and away from the observer. How about convex surface? It's a surface where the center is shaped out towards the observer. It is in opposite direction to a concave surface. Okay, so what is concave mirror? Concave mirror curve inward may be real or virtual image because rays coming in parallel as from very distant source or are all reflected to the focal length. A receiver place there will pick up the wave received over the large area of the dish instead of just the small area of the receiver itself. Okay, the picture above showing the satellite is the example of concave mirror. So, okay, now I want to explain you more further about concave mirror. For a real object between F and the mirror, a virtual image is formed behind the mirror. You see that? The virtual image formed behind the mirror. The image is upright and larger than object. This is the object. So this is the object and this is the visual image is formed behind the mirror and it is larger than the object. So the second is for a real object between C and F, a real image is formed outside of C. Real image is formed outside of C. The image is inverted and larger than the object. This is the real object smaller than the real image that is formed outside of the C. So the third situation is for a real object at C. The real image is formed at C. The image is inverted and the same size as the object. You see that the real object is formed at C, so the image is inverted and the same size as the object. The next situation is for a real object close to the mirror but outside of the center of curvature. The real image is formed between C and F. The image is inverted and smaller than the object. So that means real object is bigger than the real image. Now we look about the convex mirror. What is convex mirror? Convex mirror is curved outward reduced image, virtual image. Used as an example, rear view mirrors store security. This is not example, but it is function. Rear view mirrors store security. Because the image is smaller than the object, convex mirror reflect from wider angle than flat mirrors. Now we look about the summary table. Quantity focal length, F, positive concave length, negative diverging length. So you can see by yourself which is object distance. If positive, it is from real object. If negative, it is from virtual object. And image distance Q, if positive is real object, how about negative is virtual image. And magnification M is if the positive is will form erect image and negative will form inverted image. So height H will form erect image if positive and will form inverted image if negative. So the next one is law of refraction. The change in the direction of or bending of light rays when it travels from one optically transparent medium into another caused by a change in its speed. Like traveling from air to glass, air to water, water to air, or glass to air. There are two laws of reflection. The first one is the incident ray. The refracted ray and the normal to the surface all lie in the same plane. So the second is Snell's law. For the given media, the ratio seen I over seen R is constant. Seen I is the incident ray and seen R is the refracted ray, where I is the angle of incident and R is the angle of refraction, commonly referred to as refractive index F of the medium. So the greater the value of the refractive index N of a medium, the greater the bending effect of light when it passes from air into that medium. Now we look about different medium have different refractive index. As an example, water is 1.33, crown glass is 1.52, rock salt 1.54, ruby 1.71, diamond 2.42. So how can we get the refractive index of the glass and water? In vacuum, light travels at 300 1000 kilometers per second, whereas in glass, the velocity falls to 200,000 kilometers per second, which just means that refractive index of the glass is equal to 300,000 kilometers per second divided by 200,000 kilometers per second, which is the velocity of glass. Okay, so that's mean velocity of light through the glass. That's mean 1.5. Okay, how about for water is 1.33. Okay, what we can conclude is higher the refractive index of a medium, the slower will be the speed of light through it. This means that a medium optical density increases as its refractive index increases. Okay, so now we look about two medium, and two different medium have different density. Okay, when the optically denser medium, the ray of the light is bent towards the normal. Okay, when it is less dense medium, the ray of light bend away from the normal. As an example, as it moves from glass to air. Okay, should the ray be arranged to enter the block along the normal, which is at 90 degrees to the surface, it is not refracted. The diagram below shows a man trying to catch a fish. A fish submerged in water appears closer to the surface because of light, leaving the surface bends away from the normal as it lifts. The fish also seems shallower than it actually is. The ratio of apparent depth, this is the position of the fish, and true depth, the position of the real fish, the real position of fish is equal to refractive index of liquid and refraction index of air. If the path of the light is reversed after suffering a number of reflection and refraction, then it retraces its path. This is known as principle of reversibility of light. You can see the picture beside showing that we have shown that reflection and refraction combines together in the picture. So that means the principle of reversibility of light will form. So see that it's reversed the light. Okay, a ray of light passing from a medium into the air with smaller angle of incidence, refractive index of that medium can be written as N. It is refractive index equal to sin over R, sin R over sin I, which is sin refractive over sin I. It can be written also as actually depth divided by apparent depth. Now, we look about lens. We have two lens, which is convex lens and also concave lens. Okay, we look about convex lens. It is thicker in the center than edges. That means edges is thinner. So, the second is lens that converge, brings together, like ring. Brings together. It is mean converge, like rays. And then the last is form real image and virtual image depending on the position of the object. Okay, this is a convex lens, means that real image are formed and it will form bigger size of the image. Okay, how about concave lens? The first one is lens that are thicker at the edge, which is thicker at the end of the concave lens and thinner in the center. So, the ray of the light diverge, which is mean spread out. Okay, and the last one is all image are erect and reduced, which mean that you see the concave lens that mean they will form smaller size of the image. Next, the power of lens is the reciprocal of its focal length. Okay, so these are the formula of power of lens that you must memorize it. So F equal 1 over P or 1 over Fm. Okay, the SI unit of power is diopter. Okay, 1 diopter is the power of the lens whose focal length is 1 meter. The power of convex lens is positive and the power of concave lens is negative. Okay, so what is the formula of the lens? Lens formula is 1 over object distance plus 1 over image distance equal to 1 over focal length. That can be shown, that it can be concluded as 1 over u plus 1 over v equal to 1 over f. Okay, how about the magnification of m of any image? Okay, is the ratio of height of the image to the height of the object. That means m is equal to image height over object height. This number is a dimensionless ratio which doesn't have any units, which is m over v, m equal to v over u, which is v is image height and u is object height. Okay, how an image appears can be obtained by drawing two of the following rays. Okay, a ray parallel to the principal axis, which is refracted through the focal point F. A ray to the optical center O, assuming no deviation caused by lens thickness. A ray through the focal point F, which is refracted parallel to the principal axis, where the image is positioned and its nature, real or virtual, can be found by using the formula, where 1 over f equal 1 over u plus 1 over v, which is u is distance of object from lens, and v distance of object from lens, distance of image from the lens, f focal length of lens. And since this formula may be used for both convex and concave lens involving both real and virtual image, a sign rule positive or a sign rule negative must be applied. Next, we'll look about lens, which is, there are two basic types of lens, which is converging lens and diverging lens. Converged lens, which is separate the light rays. However, diverging lens is narrow the light rays. Okay, property for lens. Focal length. The focal length of thin lens is given by lens maker equation. You must memorize the equation below. 1 over f equal to n minus 1, 1 over r, 1 minus 1 over r2, where n is index of refraction of lens material to the medium it is in. R1 and R2 is radius of curvature of the two surfaces of the lens. Okay, sorry, this is my typo. Okay, and a positive f corresponds to a converging lens and negative f to a diverging lens. Okay, now we had done our first topic, which is light. Right, which is light. Now we look about the next topic is wave motion and sound. These are the subtopics that I want to stress about. Okay, so introduction, mechanical wave and its characteristic. And what are waves? A periodic disturbance of the particles of a substance that may be propagated without net movement of the particles, such as in the passage of undulating motion, heat or sound. Synonyms of wave can be ripple, vibration, oscillation. Okay, there are many different kinds of wave. We have 5 waves. type of wave, which is light waves, sound waves, waves on water, 6 waves, and waves along a rope or a slinky. Okay. Now we look about two types of wave that we have, which is transverse wave and also longitudinal wave. What is transverse wave? Wave that the direction of vibration of each wave particle is perpendicular to the direction of propagation of the wave. So the vibration in transverse waves go from side to side, from side to side. Okay. Example of transverse wave are water wave and electromagnetic waves such as X-rays and gamma rays. Gamma rays. Okay. How about now we look about longitudinal wave. What is longitudinal wave? Okay, wave that the direction of the vibration of a wave's particle is parallel to the direction of propagation of the wave. Example of longitudinal wave are sound waves in solids, liquid, and gases, shock wave, example a seismic wave, and also a slinky when plugged. Okay. So next is interference wave and standing wave. Okay, what is interference? It's the combination of two or more electromagnetic waveforms to form a resultant wave in which the displacement is either reinforced or cancelled. Next, we look about constructive interference, the interference of two or more waves of equal frequency and phase, resulting in their mutual reinforcement and producing a single amplitude equal to the sum of the amplitude of the individual wave. Okay, this is a constructive interference, which is the displacement is reinforced. Okay, how about destructive interference? The interference of two waves of equal frequency and opposite phase, resulting in the cancellation where the negative displacement of one always coincides with the positive displacement of the others. Okay, this is a destructive interference which the displacement being cancelled. Okay, the constructive wave and also constructive interference and also destructive interference. Okay, characteristic of sound wave. Sound wave can be described by its frequency, amplitude, and also speed. Compression. Okay, look about compression. Okay, what is compression? Compression are the regions of high pressure and density where the particles are crowded and are represented by the upper portion of the curve called crest. Okay, this is the compression, and it is also called crest. You see, this is crest. Okay, how about refractions? Okay, refractions are the regions of low pressure and density where the particles are sprayed out and then are represented by the lower portion of the curve called through. Okay, you see, this is a refraction, and you see the graph shown. Okay, the lower portion, it is shown the lower portion is called through. Okay, wavelength. What is wavelength? It is the distance between two consecutive compression crests or two consecutive throws. It is represented by the symbol lambda. Its SI unit is meter. Okay, looks. Two consecutive compression. This is compression, and which is the two crests, between two crests, and also and also two throw, which is between two throw is the wavelength. Okay, it is SI unit is meter. Okay, now let's look about sound intensity. What can you define by sound intensity? Okay, sound is a wave created by vibrating objects and propagated through a medium from one location to another. Sound travels through air or other mediums in the form of longitudinal waves. Okay, commonly acoustic wave, which is sound wave, or region of high pressure and low pressure, known as compression and also rarefaction. Okay, look the image below show that there is produced sound wave. It is sound wave from many sources. Okay, now the image beside showing that a tuning fork produces sound wave that is produced compression and also rarefaction. This is a compression and this is rarefaction. Okay, unpleasant, unwanted, disturbing sound is generally treated as noise and is highly subjective feeling. Okay, next we'll look about what is intensity. Intensity is the rate at which a wave's energy flows through an area. Sound intensity depends on amplitude and distance from the source. Okay, image beside showing that the distance from the source and also how many amplitude does it produce. Okay, so measured in decibels, which is dB. As intensity increase, so the loudness will increase, but loudness also depends on the listener's ears and brain. Okay, intensity is caused by what? Intensity is caused by the amplitude of the vibration. Okay, what is amplitude? Okay, amplitude is the height of the wave crest above the undisturbed position. Example, a student is strumming a guitar will produce amplitude, isn't it, guys? Yes, because what? Because when a student is strumming a guitar, a sound wave will produce and also amplitude will produce, and distance from the sources will cause sound intensity. Different distance from source will cause different sound intensity. Okay, next, there is table and also there is picture beside the table. Okay, this is the examples of the different source which have different intensity level, which is measured in decibel, which is dB. Okay, you can look by yourself, and also this is times greater than TOH, which is threshold of hearing. This is the common source that intensity level have 0 decibel. Okay, and this is the pictures beside showing also the same different source have different intensity level. Okay, next we'll look about frequency. What is frequency? Frequency is the number of wave crests that pass a point every second. If one crest goes by you every second, then we can say that the frequency is 1 cycle per second or 1 hertz. Okay, the frequency at which each particle vibrates is the same as the frequency of the original source of the sound wave. The human ear is capable of detecting sound wave with a wide range of frequency, ranging between approximately 20 Hz to 20,000 Hz. Okay, so When the range of frequency less than 20 Hz is known as infrasonic. When more than 20 Hz, when the range of frequency more than 20 Hz is known as ultrasonic. Okay? Look at the image beside, showing that different range of frequency will produce, what you want to say, that will produce different type, either infrasonic or ultrasonic. Okay. Number of vibration completed per second. Okay. The formula is F equal 1 over T, unit in Hertz or Hz. There is another formula that we can use instead. The question does not given of time second, which is does not given time T, and give the velocity of the sound. We can use the formula frequency equal velocity over wavelength, which means F equal to V over lambda, unit of frequency, Hertz or Hz. We hear frequency of sound as having different pitch. Okay? Low frequency sound have low pitch, like the rumble of big truck. High frequency sound has high pitch, like a whistle or siren. Okay, the image below show that okay, high pitch have high intensity and high pitch have low intensity. It depends actually. Low intensity when the volume, okay? And the below showing that low pitch have high intensity and low pitch have low intensity. Okay? Next, we'll look about simple harmonic motion. What is simple harmonic motion? Simple harmonic motion is typified by the motion of a mass on a spring when it's subject to the linear elastic restoring force given by Hooke's law. The motion is sinusoidal in time and demonstrates a single resonant frequency. Motion that repeats a regular pattern over and over again is called periodic motion. Simple harmonic motion is specific type of periodic motion that has a simple sine, a cosine wave shape. Okay? The best example of this is a spring. The more you stretch a spring, the larger the force trying to get the spring back to its original shape. Hooke's law is the principle of physics that states that the force F needs to extend or compress a spring by some distance x is proportional to that distance. That is F equal to negative kx, where k is constant factor characteristic of the spring, its stiffness. Okay? The image below shown that there is heartbeat graph and oscillating mass on a spring. Okay, and this is we call periodic motion, and this called simple harmonic motion. And this is Hooke's law, which means that the force F needs to extend or compress a spring by some distance x is proportional to that distance. How to find amplitude based on simple harmonic motion? Amplitude is the magnitude of the maximum displacement. Okay, how to find period T based on simple harmonic motion? For any object in simple harmonic motion, the time required to complete one cycle is the period T. Okay, amplitude formula X equal to A cos theta, or we can conclude as A cos omega t. Okay? So the frequency formula is F equal to 1 over T. Okay, how to find frequency? The frequency of F of the simple harmonic motion is number of cycles of the motion per second. Okay? Sound propagation. Sound produced by a vibrating object travels through a medium to a listener. The medium can be solid, liquid, or gas. When object vibrates, the particle around the medium vibrates. This process repeats in the medium till the sound reaches the ear. Okay? A wave is a disturbance which moves through a medium by the vibration of the particles on the medium. Since sound waves are produced due to the vibration of particles of the medium, sound waves are called mechanical waves. As an example, tuning fork. Okay? When tuning fork vibrates, it creates areas of high pressure compression and low pressure rarefaction. As the tunes of the fork vibrate back and forth, they push on neighboring air particles. Okay? So the picture will show the tuning fork produce sound wave and theirs have compression and rarefaction. Now we'll look about Doppler effect. What is Doppler effect? An increase or decrease in the frequency of sound, light or other wave as the source and observer move toward or away from each other. The effect causes the sudden change in pitch noticeable in a passing siren as well as the rate shift seen by astronomers. Okay, let me hear the sound effect. Okay, this is a sound effect which will produce Doppler effect. Okay, when there is relative motion between a source of wave and an observer, the apparent frequency of the wave is different from the frequency fs at the source. This change in frequency is called Doppler effect. When the source of sound is moving, the frequency ahead of it will be higher than is behind. Example, car passes over you. Okay? As it approaches, the sound becomes louder and highly pitched. As it passes, the intensity drops off and frequency decreases. Example of Doppler effect: navigation radar equipment and also police radar guns. Okay. Formula of Doppler effect is FL equal to Fs in bracket V plus minus VL over V plus minus Vs. Okay, what is the FL? FL is the frequency as heard by the listener. Fs is the frequency of produced by the source. V is speed of sound in the medium. VL is the speed of the listener. Vs is the speed of the source. Okay, we look at example 1, which is the horn is producing a pure 1000 Hz tone. Let's find the frequency as heard by the listener in various motion scenarios. The speed of sound in air at 20 degrees Celsius is 343 meters per second. Okay, so 20 degrees Celsius, we neglect it because it's not important on the formula of the Doppler effect. Okay. So, the horn is producing a pure 1000 Hz tone, okay, which is 1000 will be the Fs, okay, and 343 ms, the speed of the sound is the speed of the sound in the medium, and also 343 minus 10 is when V, the speed of the sound in the medium, which is the speed of the sound in air, minus 10. 10 is the speed of the source. Okay, speed of the source, which is the speed velocity of the horn. Okay, I produce 1030 Hz. Okay, now let's look about when the horn is still, but the human or the people move forward 10 meters per second. So that means is FL is equal 1000, which is 1000 Hz tone, in bracket 343 plus 10, which is 343 is the speed of sound plus 10. Why plus 10? It is move forward, which is 10 is the VL, which is speed of the listener. Speed of the listener move 10 meters per second over 343, which is the speed of the sound in the medium, speed of the sound in air, okay, equal to 1029 Hz. Okay, now we look about speed of sound. Okay, Air is a gas, and a very important property of any gas is the speed of sound through the gas. Okay, the speed of sound is actually the speed of transmission of a small disturbance through the gas. Sound is a sensation created in the human brain in response to sensory inputs from the inner ear. The speed of sound through the atmosphere is a constant that depends on the daily temperature. On standard day at a sea level static conditions, the speed of sound is about 760 mph or 1100 feet per second. Okay, when lightning strikes, a bright flash of light is generated. Light travels at a constant 186,000 miles per second, which means that we see the flash immediately as it happened. The speed of sound is so much slower than the speed of light. We always see the flash before we hear the thunder. Okay, the image below shows that the speed of sound is so much lower than the speed of light. We always see the flash before we hear the thunder. Okay, now we look about match number. How we can get the match number? Okay, before I proceed, I would like to talk about the history of match number. Ernst Mach researched sound wave and devised a way to describe air speeds of objects in terms of the speed of the sound. Okay, ratio of the speed to the local speed of the sound in the same atmospheric condition. Okay, this is the formula for the Mach number is m equal to air speed of object over local speed of sound. Okay, no units for m. Okay, Mach number is not fixed, depends on speed of sound in its vicinity, the area around or near a particular place. That is a vicinity. Okay, now the last one is resonance. Okay, what is resonance? Okay, the reinforcement or prolongation of sound by reflection from a surface or by the synchronous vibration of a neighboring object. Okay, excitation of natural frequency, resonant frequency by a matching external driving frequency. Okay, as an example, pushing a swing, okay, that is a resonance, and also tune box and tuning forks, that is resonance, okay, because when tuning forks vibrate, it will produce resonance, okay. See the image.